When Voyager 1 launched in 1977, no one expected it to leave the solar system. The mission had a clear and limited goal: take advantage of a rare planetary alignment and visit the outer planets. Jupiter, Saturn. Possibly more if the spacecraft survived. This alignment, known as the Grand Tour, occurs only once every 176 years. It allowed a spacecraft to use gravity assists, stealing momentum from one planet to reach the next. Voyager 1 was built for that opportunity. It was not built to last decades. It was not built to cross interstellar space. It was not built to become humanity's most distant object. Yet here it is. Voyager carried instruments designed to measure magnetic fields, charged particles, plasma waves, and cosmic radiation. At the time, these were tools for studying planets, not the edge of the sun's influence. But as Voyager passed Saturn and continued outward, engineers faced a choice: turn it off or keep listening. They chose to listen. And that decision quietly transformed a planetary mission into a boundary-crossing experiment. To understand Voyager's journey, humanity first had to answer a difficult question. Where does the solar system actually end? There is no wall, no line, no sudden border. The sun constantly emits a stream of charged particles called the solar wind. This wind pushes outward in all directions, carving out a vast bubble in space known as the heliosphere. Inside this bubble, the sun dominates. Outside it, interstellar space begins. The boundary is defined by pressure, not distance. As Voyager moved farther away, the solar wind weakened. Eventually, it slowed abruptly at a region called the termination shock. Beyond that lay the heliosheath, a turbulent zone where solar particles collide with interstellar matter. The final boundary is the heliopause, where the sun's influence effectively ends. But this boundary cannot be seen. It must be measured. And Voyager was the only instrument humanity had that could reach it. Voyager did not take a picture of the heliopause. It felt it. As the spacecraft moved outward, its instruments recorded subtle but critical changes. The density of charged particles shifted. Magnetic field directions changed. Cosmic ray intensity increased sharply. In 2012, Voyager 1 crossed a threshold. The sun's particles dropped dramatically. Interstellar particles surged. The magnetic environment stabilized into a new pattern. Voyager had entered interstellar space. This was not a guess. It was a measurement. Humanity did not declare the boundary because it wanted a milestone. It declared it because the data said so. For the first time in history, a human-made object was sampling the space between stars. Voyager 1 is now more than 24 billion kilometers from Earth. Its power is fading. Its instruments are being shut down one by one. But it still speaks. Every day, faint signals travel from Voyager to Earth at the speed of light, taking more than 22 hours to arrive. Those signals carry measurements of a region no human will reach for centuries, if ever. Voyager was never designed to represent humanity, but it does. Not because of the golden record it carries, but because of what it continues to do. It measures. It reports. It extends human knowledge beyond physical reach. Voyager did not conquer space. It listened to it. Defining the edge of the solar system sounds simple. It isn't. There is no physical wall where the sun's influence suddenly stops. Gravity extends infinitely. Light travels forever. Even solar particles thin out gradually, not abruptly. So astronomers had to be precise about what they meant by leaving. The solar system's boundary is not defined by distance, but by dominance. As long as the solar wind, a stream of charged particles flowing outward from the sun, controls the local space environment, you are still inside the sun's domain. Interstellar space begins where that control ends. This is why the heliopause matters. It marks the point where the outward pressure of the solar wind balances the inward pressure of interstellar plasma and magnetic fields. On one side, particles originate from the sun. On the other, they come from the galaxy. But this boundary moves. It shifts with solar activity. It ripples and flexes. So defining it required something more reliable than theory. It required in situ measurement. Humanity could not infer the boundary from Earth. It had to go there. Voyager 1 carried no camera capable of seeing the boundary. What it carried instead were instruments designed to feel space. Plasma detectors measured the density and speed of charged particles. Magnetometers tracked the strength and direction of magnetic fields. Cosmic ray detectors counted high-energy particles entering the solar system from beyond. Together, these instruments formed a diagnostic toolkit. As Voyager moved outward, scientists expected specific signatures: a drop in solar particles, a rise in galactic cosmic rays, a change in magnetic field behavior. Individually, none of these would be conclusive. Together, they would be undeniable. The spacecraft became a weather station for deep space, measuring conditions that had never been sampled directly before. This was not exploration by sight. It was exploration by physics. In late 2012, Voyager's data showed something unprecedented. The density of solar wind particles dropped sharply, far more than gradual models predicted. At the same time, galactic cosmic rays surged. Then the magnetic field stabilized into a new orientation. The environment had changed, not gradually, decisively. This combination of signals could not be explained by solar variability alone. It matched exactly what physicists predicted would happen beyond the heliopause. Voyager had crossed into interstellar space. There was debate, careful, methodical debate. Scientists waited. They checked consistency. They verified calibration. Only after months of confirmation did they announce the result. This was not a symbolic milestone. It was a measured transition. Humanity didn't declare interstellar space because a spacecraft was far away. It declared it because the physics of the environment had changed. Voyager 1 was only one spacecraft. There was no backup, no second opinion, no chance to repeat the experiment. Yet it was enough. Because science does not require numbers, it requires clarity. Voyager's instruments showed consistent, multi-channel evidence of transition. Different sensors told the same story. Independent measurements agreed. That convergence mattered. It showed that humanity does not need fleets to make fundamental discoveries. Sometimes, one well-designed machine, operating far beyond its intended mission, is enough. Voyager defined interstellar space not by reaching a number, but by demonstrating a change in physical reality. And that definition still stands. Before Voyager 1 crossed the heliopause, interstellar space was mostly theoretical. Scientists knew it wasn't a vacuum, but they had never measured it directly. Everything beyond the sun's influence was inferred from telescopes and models. Voyager changed that. Once inside interstellar space, its instruments detected a persistent population of charged particles, plasma that originates not from the sun, but from the galaxy itself. This confirms something fundamental. Interstellar space has structure. It has density. It has pressure. It has a magnetic environment. Cosmic rays, high-energy particles born from supernovae and other violent cosmic events, increased dramatically beyond the heliopause. Voyager could now measure them without the sun's shielding effect. This matters because cosmic rays affect everything from star formation to spacecraft electronics, and even biology. For the first time, humanity was directly sampling the environment between stars. Not imagining it, not modeling it, measuring it. Interstellar space was no longer an abstraction. It was an environment with properties, and Voyager was inside it. Voyager also answered a long-standing question about the sun itself. How far does its influence really reach? Inside the heliosphere, the sun acts as a shield. Its magnetic field deflects a significant portion of galactic cosmic rays, protecting planets and spacecraft. Voyager's measurements showed just how dramatic that protection is. Once outside the heliopause, cosmic ray intensity jumped sharply. The sun's shielding effect dropped almost instantly. This confirmed that the heliosphere is not just a byproduct of the solar wind. It is an active defensive structure, one that likely played a role in making Earth habitable over billions of years. By measuring the boundary directly, Voyager allowed scientists to quantify this protection for the first time. This has implications far beyond astronomy. Understanding stellar shielding helps scientists assess the habitability of exoplanets orbiting other stars. Not all stars create heliospheres like ours. Voyager's data turned the sun from a local star into a case study, one whose influence we can now measure, because we left it. Voyager 1 is running out of power. Its electricity comes from radioisotope generators that slowly decay over time. Each year, less energy is available. Engineers must choose which instruments to turn off. This is not failure. It is design. Voyager was built to degrade gracefully. Instruments are shut down one by one to extend the mission for as long as physics allows. Every remaining bit of power is used to send data back to Earth, measurements that cannot be taken by any other spacecraft. Even now, Voyager continues to measure plasma density, magnetic fields, and cosmic rays in interstellar space. When it finally goes silent, sometime in the 2030s, it will not be because it broke. It will be because it finished its work. And no replacement is currently on the way. Voyager remains humanity's only active probe between the stars. Voyager 1 will never return. It will never visit another star. It will never be repaired. But it continues to matter profoundly. Voyager proved something essential about humanity's relationship with the cosmos. We do not need to arrive to understand. We do not need to see to measure. We do not need to be present to learn. Voyager extended human knowledge beyond physical reach, not with ambition but with patience. It did not chase discovery. It kept listening. And in doing so, it transformed an abstract boundary into a measured reality. Voyager did not conquer interstellar space. It defined it. That is what makes it one of humanity's most important machines. Not because of how far it traveled, but because of what it taught us about how knowledge is built. One measurement at a time.